see on the screen. We're going to talk about the polymerization of alkenes. Polymerization is a word for a repeating process. A polymer is something made of individual subunits. And when we polymerize something, we're taking a subunit and we're connecting multiple copies of that subunit. So as an example, in human biochem, we'll talk about in option B, for example, we have a monomer of the biomolecules. For example, an amino acid is a monomer. We can connect multiple amino acids together into a polymer known as a protein. So here it's not quite so exciting. In this particular case, we're talking about a monomer that contains the alkene group, and we're going to keep it rather simple. Excuse me, let me go ahead and erase that. We're going to keep it rather simple and focus on a few select alkenes. You can see over here in the notes section where we're going to talk about polyethene, polypropene, and actually, I guess that's all we really need to do. I was assuming we had to do polychloroethene. Oh, there it is right there. Okay, I didn't see it. And so all this is an individual monomer repeated many times. So we'll start with the simple one of polyethene. Well, polyethene starts with a single ethene, so you could call this monoethene, I suppose. And what we're going to do is this is going to undergo reaction and create this in a repeating subunit. So we're going to connect another one onto the end here. Well, for that to happen, this carbon needs to have an available spot for bonding, as does this one, because the chain can propagate in either direction. Well, carbon in this drawing has its octet. So what has to happen is this bond, or a bond here, needs to be broken, allowing a new bond to be formed. So when that's all said and done, the original compound, shown here, I'm putting the H's on here just to make sure we see. These H's I'm drawing now are the hydrogens that were in these locations here and here. Notice I have shown the angles changing because the bond angles do change according to the Vesper theory. And there would be another group bonded in each of these locations. Typically, this is the symbolism you'll see. You see it here at the top, where this symbolism is telling us that this is the subunit repeated n number of times, and it could be hundreds, thousands of times, depending on the particular chemistry involved. So how do we go about doing this process? Well, if you remember in a previous section that we covered, I believe it was in this video, or perhaps it was in the alkanes. Yes, that's right. It was in the 10-2 video, also posted to YouTube for you guys, where we talked about the process of free radical polymerization. It was specifically with chlorine and or bromine attacking an alkane and producing a polymer of that substance. So it's the same idea here. What's going to happen is in the process of creating a free radical, basically this this compound, a free radical is formed, and that free radical will attack a neighboring compound. So as an example of what this would look like, this compound could form a free radical. And if you're not sure what I'm talking about when I say free radical, I encourage you to go back to excuse me, go back to the video I posted online about alkanes. Excuse me, I'm having trouble talking and thinking at the same time here. So go back to that video and take a look at free radicalization. So that double bond that was here consists of two bonds. As all this bond of the double bond consists of two electrons shared, and in the process of fission, we separate those two electrons, and you can make radicals. So a radical is a very, very reactive compound, and so once we produce one of these, we can connect an adjacent compound. So if we had an adjacent ethene which had not been radicalized, I don't know if that's the right word, well, this particle is extremely reactive, so it can react here, pulling one of these electrons away, forming a bond here, and breaking this bond. So I can show that by erasing this. One of the electrons from that bond I just erased was used here, paired with the electron that was present here to form this bond, and the other electron is now here, which will allow it to attack a neighbor, and this continue in this direction as well. So what you end up doing is you basically end up hooking up chains of these subgroups, these monomers. Okay. Now that's the basic idea. Now you're going to be asked, you're going to be given a repeating pattern, and you're going to be asked to talk about how that was formed. So let's talk specifically about these three. We see polyethylene, polypropylene, and polychloroethene. So we'll start by drawing the three. Here's ethene. We've already drawn that one. We had chloroethene, which is simply ethene with a chlorine group, one chlorine group. I'll draw it there for no other reason than that's an easy direction to draw it. And polypropene, which was the double bond, but the pro indicating there's a third group. I'm going to put it here just to help myself. So remember, this carbon has 3 H's. There's the third carbon. There's another H here, here, and here. So again, ethene, chloroethene, propene. Now this process is simple if you just go back to this original section here. In all of these cases, around the double bond, we will radicalize, and that's probably not the right word, but it works in this case. We will create a free radical at either end of the double bond, which can extend the chain in either direction. Okay, so this one will form a repeating pattern. There is the original compound, and the additional parts, I'll draw here in red, would be repeating patterns of those same things added in both directions. And that could go on ad infinitum. I mean, it could continue on and on. This would be polyethene. Okay. Now please notice, this was the original. Half of this bond and half of this bond. That's just symbolic representation. What I'm saying is one electron from that bond, one electron in this bond and one electron here used to be joined here in a double bond. We broke that and separated them, creating reactive ends which form chains. Okay, so here the trick to this is any side groups like this chlorine or this methyl group, treat them as if they were just some side group, just like the H's here. So we want to focus here. Here is the original grouping. I'll draw the H up instead of at an angle. And here's the chlorine. Now the attached portions, remember, half of this bond and half of that bond were from the original, and then attached is another, here's the other half of the bond, excuse me, and then here's another chlorine, H, sorry, H, and so on. And we repeat the same thing on this side. In this example down here, focus only on the double bond. What we have is the double bonded section here. There is the CH3 above. There's the H below. This H is that H. There's this H, which is that H. This H, that H. Okay. Now half of this bond and half of this bond came from that original double, and then we repeat. So here's the other half from the new compound, and so on. That is the process of polymerization. So these three, I don't know if they're going to ask you to talk about specific uses of these three, but if they do ask you to talk about them, just refer to your curriculum guide. For example, reading from the curriculum guide, reading from section 10.3.4, you are asked, and let's go ahead and scroll up there so you can see that, you are asked to include the formation of polyethylene, polychloroethylene, polypropene as examples of addition polymers. So it's common they ask you what type of polymerization this is. When it's addition, remember, addition means that the chemicals involved combine. There is no byproduct. So in this process, the chemicals that are involved was that radical. If you remember back when we discussed this part, this originally was a radical, and it attacked a neighboring ethene, and they combined. So once they combined, we had one big group. There is no loss of elements. In other words, there is no byproduct that is not a part of the group. That is addition polymerization. So you are required to know about that. So at this time, I'm going to go ahead and move on forward. If you have questions, you can always contact me via email or in class. So let's continue to the next section here on 10.5, which is the importance of these things. So it just talks about in this section, remember this does not refer only to that previous slide, which was the polymerization steps. In the previous section, we discussed the reactions that alkenes can undergo, namely hydrogenation, halogenation, hydration, and hydrohalogenation, and the purpose of those. And remember, in all cases, in those steps, sorry, let me go. Well, I'll just keep it red. In all of those steps, what we had is an addition across the bond. So in hydration, remember, we added water, and that created a 2-carbon, in this case, 2-carbon alcohol, ethanol, for example. When we added hydrogen, we call that hydrogenation. That makes an alkane. Hydrogen added across the bond. Halogenation, specifically bromination, is how we create a dihalogeno compound, or in this case dibromo compound. And remember, that is a method for detecting alkenes. Bromine is brown. As the brown color goes away, that's an indication of a presence of a double bonded carbon. And the last one was hydrohalogenation. We'll use HBr as our example, and in that case you make a monohalogenated compound, alkane. So anyway, these were the reactions we covered in a previous little section here. You're asked to indicate the economic importance of these, and so discussing those, the three that are most important is that of bromination and its use as a detector for alkenes. So remember, bromine is brown. This compound is brown. If you add a mixture to bromine water, which is brown, if the brown color goes away, that's an indication that there is an alkene present, because you're producing this, which is colorless. The second one you're required to know is that of hydration, and it is very common for the production of ethanol, for example. It is possible to produce ethanol via fermentation, fermentation by microorganisms, the conversion of glucose to ethanol and other byproducts anaerobically, that means without oxygen. That is possible in the production of an ethanol. However, it's much more efficient and quick to use a byproduct of oil refining, and many oils which have double bonds. It's very common to take those and react them with water under certain conditions and produce ethanol. So please understand that the production of ethanol on the industrial scale is done by the hydration of alkenes. And the last is that of hydrogenation, which is this one here. And a common thing here is we take vegetable oil, we take polyunsaturated or just unsaturated oils. Remember, the word unsaturated means that it contains double bonds, and we I guess I can draw something here. Remember, this is a fatty acid, so it's not exactly an oil, but some oils are basically long chains of carbons, and some of them are double bonded. This indicates unsaturated. All single bonds would be saturated. Well, the presence of these alkenes kink the molecule. So if we were to draw this more reflective, it would look more bent like this, but the presence of that double bond causes a kind of a change in that bending nature, in that regular arrangement of bending nature. So oftentimes the compound can look kinked with these double bonds present, or much less regular, I suppose is a better way of saying it. So as an example, a very straight version with no double bonds, a saturated hydrocarbon, would show a very regular arrangement, and you could pack it very close to each other. So these would tend to be solid at room temperature because of the close packing, and therefore the London dispersion forces or van der Waals forces were stronger. The double bonds cause them to kink. Here is the carboxylic acid group. So if you add hydrogen in the process of hydrogenation, you break these bonds, create this